Welcome to the sixth video of System Programming and Compiler Construction. In the previous video, I started with the fifth module, Compilers Analysis Phase. In that video, I explained you how compilers uses two different phases, that is analysis phase and synthesis phase, for converting a source program into target program. We also saw that analysis phase is divided into 4 steps and synthesis phase is divided into 2 steps. Analysis phase is also known as the front end of the machine and is machine independent, whereas the synthesis phase is known as the back end of the machine and it is machine dependent. We saw what is lexical analysis, what is the lexical analysis responsible for doing, and through an example we saw how lexical analyzer converts lexemes into a stream of tokens. In today's lecture, we will understand syntax analysis, semantic analysis, and intermediate code generation. So let's start with syntax analysis. Syntax analysis is the second step of the analysis phase. This is also known as parsing. This phase is handled by syntax analyzer. The parser or the syntax analyzer is responsible for using the tokens that are produced by lexical analyzer, and using these tokens it creates a syntax tree. This syntax tree can also be referred as parse tree. It represents the intermediate part of the machine, which basically depicts the grammatical structure of the token stream. In a syntax tree, which is also known as parse tree as I said, basically shows the order in which various operations are performed. Here, because it is a tree, every interior node or my root node will represent an operation and my children node will represent the operand of that operation, which is also known as the argument of that operation. This is basically done to make sure that the syntax of the given statement is correct. That is, every statement is written syntactically correct and it is adhering to any language's predefined rules. In case if the syntax written by the programmer is incorrect, then the syntax error stops the execution and it generates an syntax error. Let us take an example how a syntax tree is created. So this was the example which we took in the previous video. We need to convert this expression into the syntax tree based on the tokens that were generated by lexical analyzer. Now ideally, the first expression to be evaluated in this equation is rate into 60. Hence, we will first create a tree for rate into 60. So this is how the tree is created. This is already explained by me that the output of lexical analyzer is stream of tokens which goes to syntax analyzer and it is responsible for generating parse tree. So this is the tree which is created for rate into 60. Now whatever is the result of this operation, I repeat, whatever is the result of this operation will then be added to initial. Hence the next step in my syntax tree will be initial plus the remaining part of the tree. The students can also replace ID3 and ID2 with its original name, that is rate and initial. This is just to make sure that they are comfortable while they are drawing the tree. But the correct way of drawing the tree is not to use the original equations or the original name which are there in the equations, because as we see, the syntax analyzer is responsible for using the tokens that are created by lexical analyzer and creating the parse tree. Next step is to put the next parameter of the equation. So this is how my syntax tree will be created. Thus, whenever we are creating a syntax tree, we first create a tree for the execution, that is for the equation that is to be executed. Then we go ahead and the next part, and then the last part will be created or added into the tree. To make it more clear, let us take, so in this example over here, Because there is a bracket, A plus B will be evaluated first and the result will then be multiplied by C. So based on the equation, this is how my tree will be created. If we look at the next example over here, the first equation to be evaluated is the one which is in bracket. Whatever is the result of this bracket will then be multiplied by B. Whatever is the result of B into C minus D then would be multiplied by, then would be divided by E. Let us check how does it work. So my tree will be, I'll have C, I'll have D, and the operation that is happening between C and D is a subtraction operation. So this is how my tree is created for the equation which is there in bracket. This result is then multiplied by B. So it is B, the result, and it is multiplied over here. Now this entire result is then divided by E. So I write E here and I put a division operation here. Sorry. So it is a division operator here, and this entire equation is then added to A. So it is A, and then I have my plus sign. So if you observe, the syntax tree is created for the given equation. Also, if you observe, the operands are forming my children nodes, whereas my operator is either my root node or they are my interior nodes. Coming to the next step, after we have understood what is lexical analysis, syntax analysis, the output of syntax analysis, which is my parse tree, is then submitted to semantic analysis. What is semantic analysis all about? Semantic analyzer checks if the source code is semantically consistent. That is, if it conveys the intended meaning using the syntax tree from the previous phase and the symbol table. In other words, the semantic analyzer is responsible to use the syntax tree that was submitted to it by the syntax analyzer and to check whether the program conveys the intended meaning. What do we mean by that? Basically, in this step, the semantic analyzer is responsible for gathering type information. Type information means it is basically gathering the data type of all the variables which are involved in an equation. It saves this information either in syntax tree or in symbol table. And this information of based on data type is then used for creating intermediate code. Type checking is one of the important functions of semantic analyzer, where it is checking whether each operator has matching operands. That is, we know that we cannot add a string to an integer, but we can add an integer to a floating point, and the destination needs to be a floating point. So when these two type of equations are coming, when I'm trying to add a string to an integer, the semantic analyzer considers it as an error and it reports it to the programmer. But if the syntax analyzer observes that an integer is added to a floating point number and the result is saved in a floating point variable, then the semantic analyzer is responsible for converting int to float, which is known as typecasting. It automatically typecasts int to float and then stores the result to float. So this is what semantic analyzer is responsible for doing. To make it more clear, the example on the slide says, as a programmer, we know that the array index needs to be an integer. If we have declared an index to be a floating point number, then the compiler will be reporting it as an error. Another example on the slide is, the semantic analyzer will give an error in semantics when we are trying to add an integer and a string. Thus, the language specification permits some conversion, some type conversion, which are called as assertions. Assertions means the compiler or the semantic analyzer knows which data type can be automatically typecasted. Example given on the slide is a binary operator may be applied to a pair of integers or a pair of floating point numbers. If the operator is applied to a floating point number and an integer, as I just now said, I'm adding a floating point number to an integer, the compiler will automatically typecast integer into a floating number. So in this example, that is position is equal to rate initial plus rate into 60 that we started with when we saw our lexical analyzer step. In that step, it is considered that position, initial and rate all are of floating type. And 60 in this example is not in floating type. Hence, the semantic analyzer will automatically typecast 60 to float, and this modification is saved in the it is saved in the syntax tree. Since the modification is updated in the syntax tree by the semantic analyzer, the new tree will be referred as semantically verified parse tree. So this is how the semantic analyzer updates or typecast 60 to float. And the tree that is created by the semantic analyzer is known as semantically verified parse tree. This semantically verified parse tree, as I said, semantically verified parse tree goes as an input to intermediate code generation. What is intermediate code generation? It is responsible for creating an intermediate code, and it is the fourth step or the fourth phase in the process of compilation. After syntax analysis and semantic analysis, compilers generate a code which is machine-like for the target machine. In other words, it is creating a code for some kind of abstract machine. To just make you understand it, in Java also an intermediate code is created. Java is responsible for compiling a program using Java compiler, that is Javac. This Javac converts the source program into an intermediate code which is known as bytecode, and this bytecode is then submitted to a virtual machine which is known as Java virtual machine. Similarly, compilers also create an intermediate code for some abstract machine. Thus, between high-level and machine-level language resides the intermediate code. This step is necessary because generation of intermediate code will make it simple for the compiler to generate target machine code. The output of intermediate code generator is also referred as tree address code. You also call it as, in short, you can write it as 3AC. I repeat, the output of intermediate code generator is responsible for creating 3 address code, and this 3 address code is popularly known as 3AC. Let us see how 3 address codes are generated. The intermediate code generator takes as input the semantically verified parse tree. Let us understand step by step how to convert a semantically verified parse tree into intermediate code. To start with this step, we need to go to the last node of the tree, which is in this case int to float 60. For this, the code that is generated is t1 is equal to int to float 60. This entire expression in the circle will now be replaced by t1. The next nodes to be considered are id3 into t1. Creating an intermediate code for the same, the answer would be t2 is equal to id3 into t1. Again, this part of the circle, that is id3 into t1, is replaced by its destination variable, that is t2. Now if I want to get my intermediate code, obviously my answer will be id2 plus t2 is equal to id3, or t3 is equal to id2 plus t2. Again, this expression on my tree will be replaced by t3, and I will be writing ID1 is equal to T3. So this is how an intermediate code is generated, which is also referred as 3-address code. You need to notice some points that were taken care of when the 3-address code was generated. First, if you have observed, every assignment instruction has at most one operator on RHS. That is, if you observe the slide, if you have written in the first equation, that is in T1 and T3, T1 and the last equation, that is ID1 is equal to T3. The number of operator is 0. But in the remaining, if you observe, the operator is maximum 1. So when we are writing a 3-address code, we have to make sure that the operator on the RHS will be either 1 or it will be less than 1, that is 0. Thus, these instructions fix the order in which the operations are to be done. The compiler always generates a temporary name to hold the value computed by 3AC. So if you observe, int to float when was that is 60 when was converted to float, the result is saved in a temporary variable, that is T1. Further, when ID1 and T1 was multiplied, that result was also saved in a temporary variable, that is T2. In other words, whenever we are calculating something for a 3-address instruction, the result should be going into a temporary variable. Lastly, as I said, some instructions, that is the first and the last instruction, has less operands. It has less than 2 operands. It has only 1 operand. That's all for today. In my next lecture, I will be taking how to optimize the code, how to generate target code. Then we will solve an example on how the phases of compiler is responsible for converting a given equation in source code to its target code. Students, just make a note. This is a very important question and it is multiple time asked in your university exam. And then we will understand how a symbol table is managed by the compiler. Thank you for patience listening.